Yeah, in this video we're going to be operating on the qubit 1 and the qubit 0, which is in the matrix form. First we're going to be taking an identity operator. So you all know that 0 qubit will be always represented in the matrix form 1 and 0, and qubit 1 will be represented as a 0 1 as a matrix form. So you know the identity operator where the 2 cross 2 matrix of an identity operator can be represented by 1 0 0 1. So exactly the diagonal element should be of unity, and anything apart from the diagonal element, that should be a 0 in the matrix, so that we call it as an identity operator. It is 2 cross 2. If you are representing in the 3 cross 3 matrix 1 0 0 0 1 0 0 0 1, so all diagonal element should be equal to 1. Apart from that, all the things should be equal to 0. So such a kind of a representation of a matrix, we call it as a identity operator. So whenever, if you are taking an identity operator as high, or if you are operating on a qubit, it might be any 1 or 0, or it might be the superposition. If you operate on that particular qubit, it will be always equal to the qubit element in the form of a matrix. So how come? The example we're going to be taking, so please multiply identity operator along with the qubit 0. So where the identity operator of a 2 cross 2 matrix 1 0 0 1, so along with, you multiply with the qubit 0 where it has a matrix form 1 and 0. So please multiply. 1 into 1 will be always 1, and 0 into 0 will be always equal to 0. 0 1s are 0, 1 zeros are 0. So whatever the remaining term, that will be equal to 1 comma 1 and 0 in the matrix form, which is absolutely equal to the qubit 0's matrix form. So whenever you are multiplying along with the operator or the qubits along with the I operator or the identity operator, it will give the same element. Similarly, if you are operating it along with the 1, so what will be the elementary? So 1 0 0 1, and similarly, so the qubit 1 will be represented in the matrix form 0 and 1. So please multiply it. 1 zeros are 0, 0 ones are 0. So 1 zeros are 0, 1 ones are 1. So we are just multiplying a matrix. So row to column, column to row. So the remaining is 0 and 1. So 0 and 1, the matrix representation will be always equal to the operator, that will be equal to the qubit 1. So whenever you are operating, yeah, now we are talking about the Pauli's matrices. Pauli's. So Pauli's matrices are the matrices which are a set of a 3 matrix which are of 2 cross 2 order. So where it will be represented as sigma x is equal to 0 1 1 0. Second matrix, sigma y will be represented as I 0 0 minus I, and sigma y is the third matrix which will be represented as 1 0 0 minus 1. So each are of 2 cross 2 matrix. So when, if you are operating a qubits like 0, which will be having a matrix form of 1 and 0, and similarly the qubit 1 which will be having a matrix form of 0 and 1, if you are operating individually on x, y and z Pauli's matrix, so what will be the changes? So that we're going to be observing. So first we're going to be operating sigma y into qubit 0, so the value will be 0 1 1 0. So if you are operating it 1 0, the value will be 0 into 1 will be equal to 0, 1 zeros are 0, so 1 ones are 1, and 0 zeros are 0. So these are the remainders 0 and 1. So where 0 and 1 matrix will be always representing a qubit 1. So similarly, if you are operating sigma x along with the qubit 1, so 0 and 1, 1 and 0. So the qubit 1 will be represented as 0 and 1. So the value will be 0 into 0 will be 0, 1 into 1 will be 1, 0 into 1 will be 0, 1 into 0 will be 0. The remaining terms are 1 and 0 in the matrix. So 1 and 0 is absolutely representing a qubit 0. So according to this operator, whenever you are operating on the Pauli's X operator, it is like giving a exactly opposite. Means if you are operating with a qubit 0, it will give 1. When you are operating along with a qubit 1, it is exactly giving the answer of a qubit 0, like reversing. Similarly, if you operate sigma y along with the operator 0, qubit 0, so the value will be I, 0, 0 and minus I. Operate on 1 and 0, it's a qubit 0. The value will be like I1 is a I, 0 0 is a 0, 0 1 is a 0, minus I, it will be like absolutely multiplied with 0 will be 0. The value is I and 0. If you take I as a common, the representation of matrix is 1 and 0, which will be equal to I, and the 1 and 0 will be representing a qubit 0. So similarly, if you take sigma y along with a qubit 1, the manner will be same, just you need to multiply the matrix. So where the qubit 1 will be having 0 and 1, so I into 0 will be equal to 0, and 0 into 1 will be equal to 0. 0 into 0, 0, minus I into 1 will be always equal to minus I. The remaining terms of 0 and minus I. If you take minus I as a common, the operator will be 0 and 1. Absolutely minus I, 0 and 1 will be always representing a qubit 1. So it will be exactly giving the same value as a qubit when you are operating at the Pauli's matrices, which is a sigma y. So but along with that, there will be always a multiplication of I, where I is the complex imaginary number, that is square root of minus 1. So it is giving the same value. Similarly, if you operate sigma z, so sigma z will be operated along with a qubit 0, where the sigma z is 1 0 0 minus 1. So take the value, qubit 1 and 0 will be equal to 1 into 1 will be equal to 1, 1 into 0, sorry, 0 into 0 will be equal to 0, 0 into 1 will be equal to 0. Similarly, so minus 1 along with the 0 will be equal to 0. Please take the value 1 and 0. So absolutely when you are operating at a qubit 0 along with the Z Pauli's operator, so that will be giving a exactly 1 and 0, that will be representing a qubit 0. So no change. Similarly, if you are making a Z operator with a qubit 1, the value will be like 1 0 0 minus 1. Along with that, please take the qubit 1, that will be 0 and 1 multiplied. 1 0 0 into 1 will be 0, 1 0 is a 0, and similarly 0 into 0 0, minus 1 into 1, that will be like minus 1. So value will be 0 and minus 1. If you take a minus as a common in this particular matrix outside, so that will be like 0 and 1. 0 1 will be representing here exactly the qubit 1. So minus, the minus sign is representing that there is a change in the direction, that will be like a z direction, minus z direction. Unitary matrix. Unitary matrix is the complex form of a matrix. So for example, if I take U is equal to I, 2I, 1 plus I and 1. So this is like a form of a complex number. So complex number, if you are representing this type of a complex number in the form of a matrix, such a kind of a matrix, we can call it as a unitary matrix. And whenever if you are operating unitary matrix along with its conjugate transpose, it will be equal to identity matrix. What do you mean by this? So if you take a conjugate, means a good will be always having a opposite character bad, so addition will be always exactly opposite, it is called as a subtraction. So whatever the opposite thing, that will be always called as a conjugate. So if you take a u dash as the conjugate for the matrix U, that can be written as I will be having a conjugate of minus I. So 2I will be having a conjugate of minus 2I, and 1 plus I will be having a conjugate of 1 minus I, and 1 will be having a conjugate as a 1 itself because it is not a complex number. If you want to transpose this particular conjugate, so you will transpose this u dash. So it will be like changing a rows to columns to row, we call it as a transpose. So if you make it I and minus 2I, similarly 1 minus I and 1. So this particular conjugate is transposed, which we can represent as u dash transpose. Directly you can write it as u plus, which we call it as conjugate transpose. So if this conjugate transpose is multiplied along with matrix or the unitary matrix, it will be always equal to identity matrix. So identity matrix, you know that the diagonal should be equal to 1, and apart from any terms in the matrix, that should be equal to 0. For a unitary matrix itself multiplied along with the conjugate transpose will be equal to the identity matrix. For this, we will take an example where u will be 1 by 3 2 minus 2 plus I 2 plus I into 2. So we will take it as a example. So if I write a conjugate transpose of this matrix, it will become 1 by 3. So 2 will be remaining same, and this position of the minus 2 plus I will become a minus 2 minus I, and it will be transposed. Similarly, 2 plus I will become 2 minus I, and the value will be transposed. So this is the conjugate transpose. If you multiply u along with its conjugate transpose, that will become scalar 3 3s are 9, multiply it 2 minus 2 plus I minus 2 minus I and 2. Similarly, take it as plus, and this is also plus, and take the value 2 minus 2I minus 2 minus I into 2. So start multiplying. The multiplication will become 2 2s are 4 plus minus 2 plus I into minus 2 minus I. Similarly, if you multiply it, the value will become 2 2s are 4 and minus 2I, and here the value will be minus 2 2s are 4 and the value will become plus 2I. Here the value will become 2 2s are 4 and I into 2 will become 2I. Similarly, the another value will be 2 2s are 4 and minus I into 2, that will become minus 2I. Similarly, the value will become 2 plus I multiply along with 2 minus I plus 2 2s are 4. So absolutely the terms will become 0 and the remaining terms is 4. The value will be like minus into minus plus. So plus 2 2s are 4. Similarly, minus 2 minus plus, that will become 2I, and I into 2, that will become minus 2I, and I into I will become minus I square, and anything it is remainder 0 0. Similarly, here also 2 2s are 4 and the value will become minus 2I, and I into 2, that will become plus 2I, and similarly I and I will become minus I square. And I told that I is an imaginary number of a complex form, that will be a square root of minus 1. So if you make a square of this pi I, that will become square root get cancels, and the minus 1 is the remainder. Minus 1 along with the minus will be equal to 1. So the value here remaining is, by cancelling all the values, here there is another 4, we need to keep it, 4 plus 4, and the value will become plus 1, 0 and 0. Similarly here also 4 plus 1 plus 4. So totally the value will become 9. The matrix will be 9, 0, 0, 9. Take a 9 as a common. So 9, 9 get cancels. Anything is remaining, that is 1, 0, 0, 1. So 1, 0, 0, 1. So diagonal is 1, and apart from that everything is 0, that is equal to identity. So whenever you take a unitary matrix which is of a complex form, U and its conjugate transpose will be always equal to identity. So this is the unitary matrix.